Good morning. My name is Daniel Schild. I'm the president of the International Linear Algebra Society. It's a great pleasure to welcome you to the second ILAS address in person at the JMM. It's an honor to introduce to you Stephan Ramon Garcia from Pomona College here in California. He's well known for multiple contributions to operator theory, matrix analysis, number theory, complex analysis, and more. He just published his book, Operator Theory by Example, with Moshe and Ross, and the second edition on his well-known book, Matrix Mathematics, a second course in linear algebra with Roger Horn. Professor Garcia's lecture is titled Food for Thought, Fast Food for Thought, What Can Chicken Nuggets Tell Us About Linear Algebra? It's going to be an exciting lecture. We'll entertain questions at the end of the lecture, so please write them down, hold on tight. And if we have too many questions or if we want to talk more with Professor Garcia, we have reserved the room next door after we finish here so we can let the next speaker come. Thank you for coming.
Thank you. So, can everyone hear me? Okay, terrific. Thank you so much for coming to this. I know there's many things that you could be doing right now. I'd like to thank Daniel for that very generous introduction. I'd like to thank the International Linear Algebra Society for their support. And so it's an intriguing title. Hopefully that brought you all in here. I want to start with a real-world question. Let's suppose that you go to a fast food restaurant that serves chicken nuggets in quantities of size 6, 9, or 20, and for some reason you want exactly 43 chicken nuggets. What do? Well, you probably have some other problems beside this, but unfortunately you will not be able to have your hunger satisfied because the associated Diophantine equation 6x plus 9y plus 20z equals 43 just can't be satisfied with non-negative integers. So you're out of luck. Now, on the other hand, you might be able to say more is better because if you want 44 or more chicken nuggets, you will be able to satisfy your craving because using boxes of size 6, 9, or 20, you can indeed get to 44 or 45 or 46 chicken nuggets exactly. So this motivates the idea of a numerical semigroup. And a numerical semigroup, I'll define it on the next click here, but this will offend half the audience and delight some. If you're a set theorist, you're totally excited that the natural numbers include 0 for this talk. If you're a number theorist, you're horribly offended, but it's just going to make things a little more convenient for the natural numbers to contain 0. So I'm going to take a look at some positive natural numbers, n1 up to nk, always listed in increasing order. To make things work out a little bit better, I'm going to assume that they're all relatively prime. And I'm going to want to consider what fancy people might say is the free abelian monoid generated by n1 up to nk. But it's really this thing. It's the set of all natural number linear combinations of n1 up to nk. Right? So our coefficients are not real numbers or complex numbers. They are natural numbers, which include 0. So that's going to give you a collection of natural numbers. So for example, if you look at the so-called McNugget semigroup, well, you're allowed to use boxes of size 6, 9, or 20 when you're serving these chicken nuggets. So what are the quantities of nuggets that are realizable using those box sizes? Well, you can fulfill an order of 0, obviously. 6 you can do, 9, you can do 12 because you just served the person 2 boxes of 6. You can do 15, you can serve a box of 6 and a box of 9. 18, a little bit more interesting because then the person at the cash register has a couple ways of doing this. They can use a 6, and a 6, or they can use a 9 and a 9 to get to 18. So you'll see that this McNugget semigroup has some gaps in it. There's a little bit of irregularity, but there's a really interesting classical theorem which says that if I have a numerical semigroup, then every sufficiently large natural number will belong to that semigroup. So somewhere out there, there's this threshold past which all numbers of nuggets are realizable in that semigroup. So I want to now talk about cardboard boxes because I think this is the most useful way to think about things here. So think about the n1 up to nk as the allowable box sizes at your fast food restaurant. Think of n as the quantity of nuggets demanded by the customer when they show up. Now, the cashier can respond, in several ways. They might be able to say, well, sorry, I can't do exactly n nuggets. Well, Sylvester's theorem says if n is sufficiently large, you can, and you'll probably actually have more choices in how to do this. And so the cashier will respond with a collection of boxes of chicken nuggets, and will reach up to n by saying I'll have A1 boxes of size n1, A2 boxes of size n2, and so forth. That's going to be a factorization of n within this numerical semigroup. So I'm going to encode that as a vector, bold-faced A, and I'm going to want to think about the length of a factorization. That is sort of what linear algebraists would say is the L1 norm of the vector. You just add up the coefficients, no absolute values needed because everybody is non-negative. And so the way you think about it is this. A factorization is a way for the cashier to respond and fulfill this order. And the factorization length, that is counting the number of boxes used when the cashier fulfills that order. So the factorization length is counting the number of cardboard boxes used in fulfilling that order. So for example, 42 nuggets. You're allowed the classic 6, 9, and 20 sizes. Turns out that there are exactly 3 ways to fulfill that order for exactly 42 nuggets. You could use 1 box of 6, 4 boxes of 9, 0 boxes of 20. So that gives you a factorization vector 140. And the factorization length, that's the number of boxes used to physically put that order together. Factorization length is 5. Similarly, you might take the more natural approach and say, well, 42 is 7 times 6. So I'm just going to use 7 boxes of 6, no boxes of 9, no boxes of 20. Gives me my factorization vector 700. Factorization length of 7 because 7 boxes used in total. So what I want to do is study this these factorization lengths in a sort of broader, larger scale. So I'm going to need the notion of the length multiset. So I fix my numerical semigroup, and I know that every sufficiently large n can be fulfilled as a McNugget order, or a chicken nugget order. Right? So the question is, how many ways are there to do this? How much flexibility do I have? And I want to encode the associated factorization lengths in a multiset. So that is a set with multiplicities included. So an example is the best way to see this. 132 nuggets, if somebody walks in and says, I want 132 nuggets, there are a lot of ways of fulfilling that order. You could use 2 boxes of 6, 0 boxes of 9, and 6 boxes of 20. That gives me the first vector on this list. There are a whole bunch of other ways I could do this, and I hope you can see the correspondence between this list of vectors and the simplified list of factorization lengths. That first 8 in the multiset, that corresponds to 2 plus 0 plus 6 equals 8, and so forth. And I really have to deal with multisets. I have to consider multiplicity because when I'm looking at larger orders, there are probably many ways to fulfill that order, and in this case, you can see highlighted here, there are 2 different ways of fulfilling that order for 132 nuggets using exactly 15 boxes, right? So this is why we have to look at multisets. And so the general question that I want to start with, trust me, I'm going to get to linear algebra eventually. This is sort of combinatorics here. I want to describe the asymptotic behavior of this length multiset as n gets large, because I want to convert this to an analysis problem, because my background is in analysis. And a couple pictures will probably convince you that it's not as easy as it might seem. So what I have here is the histogram for the length multiset for 500 nuggets using the classic box sizes 6, 9, and 20. So what I have here kind of looks like an irregular step pyramid. And it looks like a step pyramid, but there's some irregularities, some dots hanging out in air, some holes in the step pyramid. But what this is I order 500 nuggets. I look at all the possible ways to fulfill that order for 500 nuggets, and I plot up this histogram of factorization length. So what we can see over on the left side of the screen, right? If you look at the left, you start out at 0, and that's telling us that there are no ways to fulfill an order for 500 nuggets, say with 10 boxes. It's just not possible. And if you look at the right of the histogram, your right, don't look at my hand, right? If you look at the right of the histogram, it peters down to 0 because there are no ways to fulfill that order for 500 nuggets using 100 boxes. It's just not logistically possible. In the intermediate range, some interesting stuff happens. If you look around 60, and I ask, how many ways are there to fulfill an order for 500 nuggets using 60 cardboard boxes? Eyeballing this, it looks like there are around 4 different ways of doing that, right? So some interesting stuff happens in this intermediate range. If I change my marketing strategy, and instead of 6, 9, and 20, I use 5, 6, 18, and 45 as my allowable box sizes, I get a completely different shape. It's no longer a step pyramid. It looks like it's trying to be some sort of bell curve with noise added in. Same phenomenon. On the extreme left and the extreme right, I'm down at 0 because there are no ways of fulfilling that order for 500 nuggets using too few boxes or too many. I got some interesting stuff going on in between. And this might make you feel comfortable because everyone knows that the answer to everything is always a normal distribution or something like that. It's going to be a little bit more complicated than this. Because what about this? This is like some strange, treacherous water slide with a scorpion tail at the top and a dot hanging out in middle air. Because this is what would happen if corporate headquarters says, we've got a new marketing strategy for nuggets. We want boxes of size 11 and 35, 36, and 34, right? It's a dumb strategy, but it's possible. If those are the allowable sizes of nugget boxes, this is what your histogram looks like when somebody comes in and orders 1,000 nuggets. You start out at 0 as usual, and you go down to 0 eventually, but in the intermediate thing, it looks like we got a jump discontinuity with a scorpion tail up there and some mountain peaks down at the bottom. So if you take a look at these 3 pictures, they are all very, very different. So I think this suggests that studying this linked multiset is going to be probably a little complicated. And it turns out these histograms are going to get attracted to reasonable curves that you can explicitly describe, and that's going to be our starting off point. Because let's look at more McNuggets. Now my step pyramid has more steps. What I'm doing here is I'm squashing things in horizontally. I'm scaling all of those histograms by dividing in the horizontal direction by n, the number of nuggets ordered. So what you'll see here, if I do that, I'm attracted, in this case, in the classic chicken nugget example, to what looks like a true pyramid. So again, what's going on in these histograms? I'm just normalizing in the horizontal direction so I can see what happens as I order more and more and more nuggets. Right, so that's what these histograms are. Pretty cool. You can see a strong and quick attraction to a limit curve. In this case, it's not a normal distribution, it's a triangular distribution. And to tell you the complete story of what's going on and what these limit curves are is going to require quite a lot of other stuff that's going to take us into interesting territory. We're going to need to know about complete homogeneous symmetric polynomials. So these are highly symmetric polynomials that are really, really cool. I'm going to call them CHS polynomials for short. They're going to be the sum of all degree p monomials in whatever variables you're using. I think it's easier to see with an example. Let's take a look at the CHS polynomials in just 2 variables. Well, there's the trivial monomial 1 if I'm looking at degree 0. If I'm looking at degree 1 using 2 variables, there's only 2 monomials, x1 and x2, so I add them up. Here's the interesting point. When I get to degree 2, there are 3 monomials, x1 squared, x1, x2, and x2 squared. You notice I'm not counting x2, x1 as different, right? So that's the key thing. So these are the CHS polynomials. They're super nice, very symmetric looking things that come up more in algebraic combinatorics, representation theory, and that sort of stuff than chicken nuggets. So one of the first things you can do is look at the large N asymptotics of this linked multiset. So you can look at the cardinality, that's what this absolute value means, the cardinality of that multiset. It's asymptotic to, meaning it has the same rate of growth as n goes to infinity as that thing on the right. Some power of n to the k minus 1 times a constant. That constant is highly symmetric in the generators of the semigroup, right? Perfectly symmetric. If I took a look at the asymptotic mean factorization length, right? So I basically add up all the factorization lengths and normalize by the total number of factorizations. I get something that is linear. It is asymptotic. So as n goes to infinity, the left and right sides of that squiggle tend to 1. Right? So that's what the squiggle means, asymptotic equivalence. Basically, the asymptotic mean is a linear function of n. There's some noise there, so this is only approximate. But the constant there is highly symmetric in n1 up to nk. And more generally, if I look at the moment, so I sum up the pth powers of the factorization lengths, and then normalize by dividing by the total number of factorizations, that thing is asymptotic to n to the p times a constant. Now, who cares what the constant is? The only thing that you need to know is that constant is something involving, well, a binomial coefficient and these CHS polynomials in the reciprocals of the generators. So some symmetric function of the reciprocals of the generator seems to be governing the large-scale statistics here. And the proof of this moment formula is actually kind of fun. It involves a lot of multivariable generating functions, some combinatorics, some complex analysis to do some residue computations. I just want to put this here as important formula. Not that you have to memorize it. The one thing I want you to know about this formula is we know what the moments of the length multiset are asymptotically. We know what happens to them as n goes to infinity, roughly speaking. What happens to them? You get some power of n, but the multiplier, that constant, is a CHS polynomial, complete homogeneous symmetric polynomial in the reciprocals of the generators. So the CHS polynomials show up there when you're studying the large-scale asymptotics. So the GUI theorem, right? GUI in several ways, but that's the name of the authors, basically says this. Well, we suspect that, studying factorization lengths, it sort of grows linearly with n, so n is the right scale to look at things. So if I count the number of factorization lengths that are in the interval between alpha n and beta n, I compute that ratio and let n go to infinity, I get a simple expression, integral of some function from alpha to beta. The important thing is that function is totally explicit and really cool. That function is equal to this giant mess. So the thing I want you to recognize about this giant mess, it's got absolute values in there, right? And the presence of that absolute value is going to mean that I have some behavioral transitions when I reach 1 over a generator, right? Because that's going to force the thing inside the absolute value to be 0, where I have that sort of transition. I got that corner point. So this thing, it turns out to be a probability density function. That means it's non-negative, integrates out to 1, and in fact is actually compactly supported. So it's a reasonable thing. It looks kind of ugly. Linear algebra folks will say, hey, there's a Vandermonde determinant in there, and indeed there's a Vandermonde sort of interpretation. There's a determinantal form that I don't want to go into. Important thing here is the smoothness increases the more generators you have. So ck minus 3, what that means is you are k minus 3 times continuously differentiable. Right, so you're smoother and smoother, you have more and more derivatives, the more generators you have. And so people who are fans of probability and Fourier analysis and stuff will kind of recognize what was going on in the background. I have the moments, asymptotically, so that means I can attack the so-called characteristic function, from probability theory, and then try and invert that using Fourier analysis, which is how one gets to this explicit function. And that also means you sort of have weak convergence in the sense of probability theory, so which means you can attack your factorization lengths with whatever continuous function you want. So that can get you towards some more exotic statistics if you want. But anyways, the thing to keep in mind about this GUI theorem is there's this master function which governs the length multiset. And we know exactly what it is, and we can write it down as ugly as it looks. And so we can do stuff like this. Let's take our ridiculous semigroup where I have box sizes of 11, 34, 35, and 36. If you work out what that function on the previous slide is, it's that thing. It's a piecewise quadratic. Its transitions are as predicted at the reciprocals of the generators. It turns out it's a probability density function. And using this, you can work on the continuum side. Instead of counting stuff and computing stuff, you work on the continuum side, and you can do things like, well, I can take a look at the median of this probability density, capital F, figure out what it is, and then I know I need to scale it by n to get the asymptotic median. So I can get something like this, that for this semigroup, as n goes to infinity, the asymptotic median factorization length is that ridiculous linear function. And I think it would be hard to figure out what that constant factor is there without being able to work on the continuum side and being able to throw this capital F function into Mathematica and have it grind it out. You're not going to see this ridiculous, constant there by just counting stuff and trying to, extrapolate from the discrete side. And so let's go back to our scorpion slide with the mountains at the bottom. So I'll take a look at my normalized histograms. We should see attraction to a limit curve. That limit curve, it's supposed to be ck minus 3. K is 4, the number of generators, so this curve is C1, meaning those are not corners. This curve is actually 1 times continuously differentiable. And we see eventual attraction as I order more and more nuggets. I get attracted to this limit curve. And it's pretty interesting. You can begin to see, even on that very vertical part where there are a few dots, as I order more and more nuggets, these scaled histograms basically even fill out that really sharp vertical thing. The important thing to note, this is a C1 curve. Those are not actual corners. And so, as I said, you can work on the combinatorial side, just order 100,000 nuggets, find all the possible ways to serve it, and then look at all these statistics on factorization length. You get the left column. You can work on the continuum side and say, well, I can just work with this length density function, that capital F, and figure out what my predictions for ordering 100,000 nuggets are. And you can see you get almost exact agreement with all the key statistics, mean, median, mode, and all the other sort of more exotic things that you might want to look at. So pretty cool. You might say, what does this have to do with linear algebra? I'll eventually get there. You might say, where have I seen this function before? Probably nowhere. Some people have seen it, right? So, okay, this length density function is this strange looking thing. It's piecewise polynomial, degree minus 2, and it has these transitions at the reciprocals of the generators. And it also gets smoother and smoother the more generators you have. It turns out this is a Curry-Schoenberg B-spline from spline theory, which originally started as approximation theory or as a topic in approximation theory, but gradually, because of its important applications, it's now thought of as part of computer-aided design. And so, what are splines? Who cares? Well, they allow you to solve a lot of really interesting interpolation problems. You can interpolate a finite set of values with piecewise polynomial functions, subject to a whole bunch of constraints that you might want to impose. So I'll give you a picture which indicates why you might want to do this. Let's say I have 6 data points, and I want to connect them with a smooth curve. So one way of doing this would be with so-called cubic spline interpolation. So this means I'm going to interpolate this data with a piecewise cubic function. So I'm cubic on each interval between the nodes. And they're glued together in such a way that the resulting function is C2. It's 2 times continuously differentiable. So it looks smooth, it looks appealing. And this cubic spline interpolation is used in the real world with data points and higher dimensions to model things like car hoods, airplane, this sort of stuff, because it has some nice looking results. I can't tell that that's not an infinitely differentiable function. I can't tell looking at it that that's not a polynomial. It's a bunch of cubic polynomials just glued together in a clever way. So, and again, this is sort of a linear algebra question. How do you do this? You might think about that. The classic interpolation theorem from linear algebra is the Lagrange interpolation theorem, which can be proved either using basis polynomials or Vandermonde matrices. Vandermonde is going to do something different. It's going to say you've got 6 points I want to interpolate with a function. I'm going to do that with a single polynomial. Turns out the degree will be 5 or less, or you can do it with degree 5 or less. And I have a single polynomial that passes through all of those points. Now the polynomial is going to do some wild stuff away from the control points, and you can sort of see when you compare the spline interpolation with the Lagrange interpolation, clearly one is much better for industrial purposes, right? One of them is going to make much more aesthetically pleasing and probably useful car hoods or airplane wings than trying to use Lagrange interpolation. So this is why spline theory is often thought of as part now of computer-aided design. And so in Curry-Schoenberg's paper where they study B-splines, they have a couple of interesting things. The paper is from '66, but they say, well, we actually wrote it in '46 and finished it in '47 for no good reason. An interesting thing, I think back in the mid-40s, really computing was in its infancy, so they were studying this problem in interpolation theory and functional analysis, and in the 60s, you actually do have computers and you could do that stuff, so I think maybe they recognized that, oh, this stuff is actually really useful in a lot of purposes. And so their original interest in this studying those weird functions was the study of so-called polyfrequency functions. There's a nice geometric interpretation, which I'll circle back to, which is you can recognize that these B-splines are actually probability densities that are attained or obtained by taking a high-dimensional polytope of unit volume or unit hypervolume and then projecting it down to an interval. So it's kind of a cool interpretation. So you can attack some of these things using more geometric means. It turns out that that same function is also called Peano's kernel when you go back over 100 years to the theory of divided differences, which is a really hot topic over 100 years ago. And Schoenberg even says, well, these things were actually known to Hermite and certainly Peano. They also seem to be known to Laplace. So these weird functions that showed up in the study of numerical semigroups seem to have appeared every 100 years or so. And Schoenberg even says, well, splines actually have their seed in some ideas of Euler from the 1700s. So historical roots of this are pretty deep. I kind of suspect that had Curry and Schoenberg been interested in numerical semigroups, they would have been able to get our theorem using totally different methods. And it may, in fact, be buried in some paper of theirs. So different route, but now we're going to go in some different directions here. So let me first tell you about a couple improvements or different directions you can go here. A factorization is a way to fulfill this nugget order. We encode that with a factorization vector A, and we look at the factorization length. We add up the elements of A. So from a linear algebra viewpoint, that's taking the dot product of the vector A with the 1, 1, 1, 1, 1 vector. Right? When you add up the entries of a vector, you're dotting it with the all ones vector. So a couple of things you can do is take a look at lengths modulo m, and there's some really cool equidistribution results that happen there when you sort of throw in some number theory. Now, it also makes sense to use sort of more traditional geometric techniques, point counting and polytopes and that sort of stuff, to make the GUI sort of theorem. It's GUI because the history is kind of murky, and it seems like everybody's rediscovered this every 100 years or so. You can use more general functionals. Instead of dotting with the all ones vector, you can dot with whatever vector you want. And more importantly, you can get the decay rate, you can get the error bound completely explicit. So we're able to do that for 3 generators and now with 4 generators and higher. But I want to revisit those CHS polynomials because they're really cool. Complete homogeneous symmetric polynomials, it turns out, 1977, were shown to be positive functions, meaning if you plug in a non-zero vector into a CHS polynomial, you get something positive if the degree is even. So for example, there's the CHS polynomial of degree 4 in 2 variables. That is positive everywhere away from the origin. And you might say, well, that's obvious, it's a sum of squares. No, it's not a sum of squares. Take a look at those red terms, those things can definitely be negative. So Hunter's positivity theorem, that the even degree CHS polynomials are strictly positive functions, has some non-trivial content because there's some squares in there, which are definitely positive, but there's some negative stuff. So there's some fight going on, but the positive stuff always wins. And when you Google something, often one of the first sources is Terry Tao's blog. So that's where I first learned of Hunter's theorem. And in the comments, one of the things he said, well, is there a probabilistic interpretation of Hunter's theorem, essentially? Because that's, probabilistic interpretations are often one way of proving that this or that is positive, because it's a probability or related to a probability. And it turns out that that kind of falls out of the junk that we did. And so forget about semigroups entirely. Forget about nuggets. Who cares about those? If we just forget about the origins and write down essentially what the f function would be for arbitrary generators, real numbers, x1 up to xk, or up to xn, you get this function. And it has all the usual properties. It's a probability density. And, what happens there? Well, I mentioned on that important formula, the moments are tied asymptotically to the CHS polynomials, right? The pth moment of this capital F function is the pth CHS polynomial in the variables x1 up to xn. So what happens here is kind of cool. We've got this formula here that says the CHS polynomials are moments of some probability density. And we say, wait, F is a probability density. It's always non-negative. So if P is even, I'm integrating some positive stuff. So the result is positive. And that basically gives Hunter's theorem as a corollary. It's a probabilistic interpretation of Hunter's theorem there. I think there's a better one that I'll explain later on, but it's kind of cool. So now linear algebra. I promised linear algebra. Hunter's positivity theorem immediately suggests that I use that positivity for some purpose. Hunter's theorem says the even degree CHS polynomials are strictly positive. So if you plug in something non-zero, I get something positive. So why don't I screw around with matrices and eigenvalues? So I'll take a look at the set of Hermitian matrices. So a matrix equals its own conjugate transpose. So for students, star is the conjugate transpose. If you're more comfortable with real matrices, just think of real symmetric matrices, A equals A transpose. So a Hermitian matrix has real eigenvalues, and you can list them lambda 1 to lambda n. And so I've got these real numbers, the eigenvalues of some typical Hermitian matrix. I can throw it into a CHS polynomial. And it turns out it's more than just a positive function. It actually defines a norm on the Hermitian matrices. Because if you plug in the eigenvalues of your Hermitian matrix into your CHS polynomial and take the appropriate root, you get a norm on the Hermitian matrices. That means what satisfies a few axioms. Triangle inequality is the trickier one. I'll try and touch on that in a little bit. So look at these weird norms. I want to connect this to some things that some of the linear algebraists will be a little happier with, and some of the operator theorists will like, and that is connecting this to trace polynomials. So the trace of a matrix for the students, that's the sum of the diagonal entries of the matrix. It seems like a silly thing to do, but one of the important things about the trace of a matrix, the sum of the diagonals, it's also the sum of the eigenvalues of the matrix. It's a pretty remarkable, cool fact. So, okay, the CHS polynomials are symmetric functions here now of the eigenvalues. So one of the things you typically do when you're dealing with symmetric functions is write one symmetric function in terms of the others, right? There's a lot of symmetric functions out there. The so-called power sum symmetric functions are some of the favorites, and those will rise here as traces of powers of A. And so you can write all of this stuff as polynomials in traces of powers of your Hermitian matrix A, and you get these weird formulas. So believe me, a lot of people are happy with these sort of formulas and excited. It's sort of a traditional thing to do in sort of operator theory to convert things into this fashion. Important thing, I can compute all of these without knowing the eigenvalues now, because the trace is just the sum of the diagonal entries of a matrix. So I don't need to know the eigenvalues if I have these trace representations. So I got all these weird norms coming from Hunter's theorem. And the positivity alone is a delicate matter because Hunter's theorem is a non-trivial result. So if I take a look at the trace polynomial representation for the fourth power of the 4 norm, the CHS 4 norm, I get this ridiculous thing. Now it's ugly, yeah? But the important thing is I want to point out it has some stuff in there that can definitely be negative. So it's not a matter of just adding a bunch of positive stuff and getting something positive. There's a fight there, and I got some stuff that can definitely be negative. Now, other thing to note is the CHS norms, as I've defined them, don't involve absolute values of eigenvalues. So people who do spectral graph theory or people who do a lot of linear algebra will recognize, oh, but that's a little bit different than most of the norms that I deal with. Most of the times, if I'm looking at a norm on Hermitian matrices, I immediately put absolute values on the eigenvalues. Not the case here. We're using the raw eigenvalues themselves. And so that means that these norms can sometimes distinguish what are called singularly cospectral graphs. Right? Graphs that have the same singular values, but we can detect, we're not using absolute values. Basically makes this a little bit different than most norms than one looks at. The triangle inequality is going to be a little hard to establish because let's face it, if you give this to a linear algebra class and say, here's this giant expression, prove that it satisfies the triangle inequality, it's not going to work out, right? So one reason, morally speaking, it makes sense that the triangle inequality is not trivial is because you're talking about a relationship between the eigenvalues of A, B, and A plus B, where A and B are Hermitian matrices. And the complete story of the relationship between the eigenvalues of A, B, and A plus B was not completely known until around 25 years ago. It was a famous problem called the Horn conjecture, solved by Klyachko, Knudsen, and Tau about 25 years ago, so an important result. Now, for the International Linear Algebra Society people here, that is not Roger Horn, that is Alfred Horn. Everyone thinks it's Roger Horn, the matrix theorist. It is Alfred Horn. So morally speaking, it's probably going to be difficult. Now, I want to get back to a different probabilistic interpretation of what I was talking about earlier. We'll have vector xi, where the entries are going to be independent, standard exponential random variables. A lot of words there. What it basically means, the entries of my vector are random. Random in what sense? Well, they're going to be governed by this probability density. So this function, basically 0 if I'm on the negative part of the real axis, and then it starts with this exponential drop once I get to x equals 0. And it's a probability density, it's non-negative, integrates out to 1, so it's a perfectly legitimate thing for me to draw random numbers from. So xi has all these random numbers drawn from this distribution here. So what one can do is a grotesque computation, which, you know, if you're not a fan of probability theory, you can kind of ignore what I'm going to do here. But it's standard textbook stuff. The expectation of the kth power of a standard exponential random variable is k factorial. You can find it in any probability theory book. So if I take some other vector x, whose entries are x1 up to xn, and I dot it with my random vector, I get some interesting stuff happening. So I take the dot product of my random vector x, or sorry, my random vector c, and I dot it with this fixed vector x, raise that dot product to the dth power, I get a bunch of junk that you see on screen, right? So I take the expectation of this, and again, you can tune some of this out, but I'm going to say this for the people who do probability theory and stuff here. You basically hit this with a multinomial theorem, use the independence to break up the resulting expectations, use the formula for the moments there where you get the k factorial above, and everything cancels out, and you're left with essentially a constant times the CHS polynomial of degree d. So it's a interesting result. I can't claim that we did it. I mean, it's a known result. So it's sort of a better probabilistic interpretation, I think, than the other one. It's kind of straightforward. It's a nice little computation. But essentially, what do we have here? The CHS polynomials evaluated at some vector x, it's essentially an expectation of something positive, because d is going to be even in what I'm going to do next. So we get Hunter's theorem again. The positivity of the CHS polynomials follows because I'm taking the expectation of something that's guaranteed to be positive. And so it also gives us Minkowski's, it gives us the triangle inequality via Minkowski's inequality for expectation. And you might say, oh, well, I thought you said that's going to be hard. Well, it is, because this, I'm applying this to vectors, right? I'm not doing it for eigenvalues of matrices, because we all know that if I have A and B, and I know their eigenvalues, I don't really know what the eigenvalues of A plus B are, right? So this is the triangle inequality for the trivial case where I guess I'm using diagonal matrices, right? But so it shows that, even that so-called trivial case is not really that trivial. So anyways, that's a probabilistic interpretation. Those of you who aren't fans of this, just remember, there's a probabilistic interpretation of the CHS polynomials and Hunter's theorem, and hence the fact that those CHS norms are actually norms, right? And it's connected to the standard exponential distribution. So being an operator theory person, I don't like commutativity. I don't like powers of A to commute with each other and that sort of stuff. So I want to mix things up and make them non-commutative. And that's going to involve a bunch of other stuff. So I don't want just A and powers of A. I want powers of A and powers of A star, the conjugate transpose of A. And that's going to lead us to some interesting things here. So this result is going to take a little bit to work through. Pi is a partition of D. D is going to be some even number. So by a partition of D, I just mean that the entries of pi, pi 1, pi 2, etc., have to sum up to D, right? So it's a way of breaking D down as a sum of smaller natural numbers. Pi for partition, right? And I got these words. Okay. So let me talk you through what these words are. So imagine D is kind of large. Like here it's somewhat more than 15, right? D is large. So you write down a bunch of A's. You write down DA's in a row, right? So you A a bunch of times. And then what I can do is package all of those A's in various ways. And I'm going to package them according to this partition. So I'm going to group pi 1 of those A's together, pi 2 of those A's together, and so forth. And then I'm going to take the trace of those packages. Right? So that's how a partition is going to lead me to a product of traces of powers of some matrix A. Right? Okay. It's not clear that this is going to do anything useful or anyone should care about it, but trust me, it's going to be pretty useful. So now that we've taken our partition and gotten this package here of products of traces of powers of A, I want to sprinkle in some dust here. I want to sprinkle in some adjoints, conjugate transposes. So those are denoted with the star, the asterisk. And so basically, I want to make half of those A's in there decorated with stars. So I want to turn them from A's to adjoint of A. And there's a bunch of ways to do this. What I want to do is then average over all possible ways of doing this, and I get this capital T sub pi nonsense. So the moral of the story, if you do all this partition combinatoric stuff and trace polynomial stuff, you get a norm, not on the Hermitian matrices, but more interestingly, on all complex matrices. And I think it's pretty interesting that that thing happens to be a norm, meaning it satisfies the triangle inequality, and it works for all complex matrices. And its origins, wait a second, that had to do with McNuggets way back then, and symmetric functions. You know, it's a wild ride to get to here, right? I mean, you could never have told when I asked you about packaging chicken nuggets that it would lead to sort of these strange norms that are combinatorially inspired here. But interestingly, now I got these norms on all the Hermitian matrices. And it turns out that these are generalizations of the CHS norms. And so let me do a quick example when d is equal to 2, because the combinatorics is essentially trivial. Because d equals 2, I don't have many partitions to play around with, right? So there are only two partitions of 2, just 2, which is not exciting, and 1 plus 1, which is not exciting either, right? So those are the two partitions I have to worry about. Why do I need to worry about partitions? Because in the definition of these weird norms, I have to sum over all possible partitions of d. And that sort of tells you why I'm using d equals 2, because you get more and more and more partitions as d is larger. So I have those weird constants, right? This z sub pi. Now, this z sub pi looks like a strange-looking thing. I'm going to try and convince you it's not really a strange-looking thing. It's an innocent constant. People who play with symmetric functions in representation theory will be totally cool with this, because it kind of looks like something familiar from that theory. But the idea is this. I take a look at the partition 2. OK, how many times does 1 appear in that partition? Well, the answer is 0. How many times does 2 appear in that partition? Well, 1 time. So you can sort of see where that z of the partition 2 simplifies down to 2. Right? If I look at the partition 1, 1, what happens? OK, I ask myself, how many times does 1 appear in the partition 1, 1? Well, the answer is 2. How many times does 2 appear in that partition? The answer is 0. So you just need to count these things, and that'll give you these z constants. Believe me, they get more exciting when d is a little bit larger, but we don't want excitement here. So now this averaging process that I mentioned, it's actually not that hard when I'm dealing with d equals 2. Well, OK, I'm going to have two a's. There's not much I can do with those two a's. And I'm going to want to sprinkle in stars on half of them, but there's only 2 of them. So that means I need to essentially average over the number of ways to put a star on one of 2 a's. So not too much is going to go on there. So that's going to give me this t expression from the previous slide. So for the partition 2, what do I get? Well, I'm going to average over all possible ways to sprinkle 1 star among 2 a's and then take their traces. So I'll get something like this. Now that last equality is because the trace has this nice cyclic invariance property. So trust me on that. For the other partition, well, now I have trace A, right? And then I want to sprinkle 1 star among them. So I average over that, and I'll get trace of A star times trace of A. And so that gives me, in this case, the square. I got rid of the square root. That gives me the CHS2 norm on all the n by n complex matrices. Kind of weird, but you can see it's kind of a nice formula, and it's not obvious at all that these things should satisfy the triangle inequality. Cool fact, if A is equal to A star, if I'm dealing with a Hermitian matrix, or a real symmetric matrix if you're more comfortable with that, it reduces to that CHS norm, which was about the eigenvalues of your matrix. And so let me give you a gross example here. So this is a horrific thing, and you've already tuned out. But trust me, there's a reason to look at it. I don't want you to look at the structure other than say, wow, that's really ugly, and I would never think that that has any good properties at all. Satisfies the triangle inequality. It's a nice thing. That's a norm on the n by n matrices if you take the 4th root there. So it's going to reduce down to that CHS norm in the Hermitian case, right, that we got from Hunter's theorem. Right? And here's why. Because I've color-coded things, and you can see if A is equal to A star, in other words, if we're in the Hermitian case, all the green stuff collapses to the green stuff in the second equation. All of the teal stuff is going to, or I guess cyan stuff, simplifies down to the cyan stuff. The orange stuff simplifies down to the orange stuff below, and so forth. So what we really have is a nice non-commutative extension to all complex matrices of this norm that we originally got on the Hermitian matrices alone using the CHS polynomials, which came from looking at the asymptotics of factorization lengths and numerical semigroups. So it's a long story here. But it all boils down to generalizations of some facts that we had at earlier levels. And there's another direction we can go here. You can say, hey, wait, there was that slide I ignored about exponential random variables, right? And I said, well, the CHS norms, or the CHS polynomials, were moments, essentially, of a standard exponential distribution, when I put them in a random vector and did all that stuff a few slides ago. You say, well, what's so special about exponential random variables? Why don't I just use whatever random variables come to mind and see what happens? And in fact, you can do that. And some of my collaborators and I are now sort of developing this sort of theory of random norms, right? If I have a random vector whose entries are drawn from whatever distribution I want, I should be able to come up with a version of Hunter's theorem and some strange norms in this fashion. And in fact, that's what we're doing. It's pretty cool stuff, kind of incomplete at this moment. I want to change tack a little bit to our final topic, if this works. And that has to do with operator algebras. And operator algebra scares a lot of people because the prerequisites to study C-star von Neumann algebras are so high. It's like up here, even I don't know about them. But I know how to stuff boxes inside each other. So here's the idea. We're going to look at M sub n. That is the algebra of complex matrices. When I say algebra, what do I mean? I mean, I can multiply stuff, I can add them, and I've got an action of a scalar multiplication, and everybody's all compatible, right? So it's a nice algebraic structure, the set of n by n matrices. And so what I want to do is, okay, fancy talk here, I want to stuff matrix algebras inside other matrix algebras. That's what's going to happen here. And I want to do it in a unital way, and in a way that preserves algebraic structure. So unital, meaning identity preserving. I want the identity matrix over here to go to the identity matrix over here. I want it to be a homomorphism, meaning I want the algebraic structure to be respected. And if I want to stuff matrix algebras inside one another, the only real constraint is common sense. And I'll give you an example here. So let's take a look at, on the left side, I have a block diagonal matrix, A, B, right? Where A is of size n1, B is of size n2, right? So that block diagonal matrix belongs to the algebra mn1, direct sum mn2. Now, if I want to, stuff a homomorphic image of that algebra inside another algebra, I just need to make sure that the sizes make sense, right? So what's going to happen, up to some notion of equivalence, this homomorphism has to do something like this. It's got to stuff some copies of A on the diagonal and some copies of B on the diagonal. And in order for this map to be unital, meaning I don't have any extra space where I have some zeros on the diagonal in the big matrix, in order to make this unital, for the identity to go to the identity, the box sizes have to match up. Right? So in this example, you can see the sizes have to work out. So the size of this big algebra that I'm stuffing things into, well, in this case, it's 2n1 plus 3n2. It looks like a numerical semigroup sort of idea. And in fact, that's really the main constraint there, is the box sizes have to make sense. So C-star algebras. It's a field in operator algebras. It's often thought of as non-commutative topology. It's a totally fascinating topic. I'll just only be able to brush through some very trivial stuff here. One cool way of generating C-star algebras, the so-called approximately finite dimensional C-star algebras, is to stuff matrix algebras inside other matrix algebras and do it over and over and over again. So you have this infinite tower of algebras, and then you take the closure with respect to some inductive limit topology, and in the end, you've got this really cool infinite dimensional algebra that has a lot of awesome properties. So that's kind of a standard way of doing things, just stuffing boxes inside other boxes and continuing forever. And so we can imagine, can numerical semigroups and all of this other stuff tell us something about approximately finite dimensional algebras? And in fact, we can do something here. Because let's say I have a unital homomorphism from a direct sum of a bunch of matrix algebras into some other bigger matrix algebra, right? And it has to be unital, identity preserving, it's got to be homomorphism, et cetera. So one can show that up to a totally natural and standard notion of equivalence, you're basically stuffing diagonal blocks onto other diagonal blocks, possibly with multiplicity. Like we had an A, we went to an AA, or we had a B, it goes to BBB on the diagonal. That's the only way to really do it, up to some standard notion of equivalence. So the dimension constraint is this, the dimension of that big algebra that you're stuffing things into, that size n by n, well, that n has to equal some number of multiples of n1 plus some number of multiples of n2 and so forth. That's the numerical semigroup condition, right? That's a factorization of n in a numerical semigroup. And for large n, we kind of know exactly what happens because we can answer all questions about factorization lengths in numerical semigroups. And so we kind of know what happens as phi ranges over all such homomorphisms. So what one can do is a cool setup here. Now, some of you might object and say, wait, but didn't you require the generators to be relatively prime? Didn't you require the generators to be distinct? Yes, that's true. That's why I also snuck in on a slide a little while back saying that we got these generalizations, we can do these more general functionals, and in fact, we can even have repeated generators. I had this slide with colored numerical semigroups, meaning I can even have repeated generators. I can have a red 2 and a blue 2, a green 3, a pink 3, right? So I can do that sort of stuff. So don't worry about that. What we'll be able to do is attack algebras that grow sufficiently rapidly. So think of G sub r as something that gets big really, really, really quickly. Think of G sub r as r factorial, right? So r factorial blows up so quickly when I take the ratio of two successive factorials, I'm blowing up to infinity, right? So these G sub r's are growth constants that sort of get big really quickly so that their quotients, gamma sub r, tend to infinity. So what I'm going to do is I will take an algebra at each level r, and that algebra is going to be the direct sum of a bunch of other matrix algebras. So now I have a whole bunch of algebras, A1, A2, A3, A4, et cetera, and they're getting big at a colossally fast rate. Right? So what one can do is say, like, okay, if I have a unital homomorphism from the r minus first algebra into the rth algebra, the only real constraint here, up to some natural notion of equivalence, is the dimensions have to make sense, right? The box stuffing has to agree so you don't have any padding left over. You don't have any zeros left on the diagonal when you stuff matrix algebras into other matrix algebras. So you get this system of equations here. So these are just the dimension constraints. It's just saying that the boxes have to fit correctly. Now, interestingly, this is well, it kind of looks like a numerical semigroup thing in parallel. What happens here for these nested algebras, if I divide by G sub r minus 1, I clean up the left side, and then I just have gamma r's on the right times those semigroup generators, right? So the dimension constraints give me these sort of parallel numerical semigroup equations. And of course, if my algebras grow at a phenomenal rate, gamma sub r is tending to infinity, so the asymptotics should begin to take over, and I should be able to say a lot about, say, random C-star algebras drawn from this ensemble that I'm building here. And I should be able to say things about what's happening on average at every single level. I should be able to talk about mean, median, and mode sizes of how many different blocks are in each level. And I should be able to do all sorts of stuff. Now, I say should be able to because we haven't, we're still thinking about it. But that's work in progress. So I'm almost done. I thank you for the smattering of applause that was about to begin. I want to end with something totally self-serving here. Shameless self-promotion. Check down in the Oxford and Cambridge booths. There's a cool book on operator theory just out, and there's also the second edition of the Matrix Mathematics, the second course in linear algebra book that I wrote with Roger Horn. That'll be down there. And what I'm going to leave you with is the bibliography. So if you want to learn more, check out those papers.
Questions? Questions? You can come to the microphone and ask your questions on either side.
Ask a question. Is this on? Yeah, you can hear me, right? I really liked your computational parts where you were showing the different graphs of how many ways the length factorizations, I think you called them. How much does computing factor into your work, and what kind of computing software do you use?
Great question. Let me see if I can get back to, okay. Well, I'll talk while I'm mindlessly clicking on this here. So that's an interesting thing. So I'm a Mathematica person. One of my co-authors, Chris O'Neill, is a Sage person. So we were attacking both ends. I was attacking the continuum side. 'Cause I'm sort of the natural analyst in that group. He's the combinatorist in that group. So he likes doing the computations in Sage. I can't speak to how he was writing his algorithms, but I can certainly say that he was the one that was grinding out the combinatorial side and doing the actual counting to produce this sort of stuff. I was working on the continuum side. I don't think, you know, in terms of algorithms, it's terribly complicated. I don't think we're revolutionizing anything in terms of the computation here, but you know, it's certainly fun stuff, and it's cool, and it's very gratifying. And you can't imagine how elated I was when, you know, the first sort of formulas came out, because you're never going to get a closed form formula for anything once. You know, let's face it just doesn't happen, right? You don't get closed form formulas. And when I was working on this, I was at ICERM doing something else. I stayed up till like 3 in the morning working on this, and I realized, wait, there's an explicit formula. There's no way, that can't possibly be true. And when I plotted it and I got a perfect match, that was you know, a revelation for me. I was shocked that something could work out so cleanly. And yeah, but so it's a fun thing, but I can't say that we did anything revolutionary computationally.
Thanks, great talk. I had a question about your the piece where you drew from these exponential distributions to compute the connections with the CHS polynomial, I guess. I may be mistaking that, but have you, yes, this part. Yeah, this is very interesting, but in a completely different setting, we know that if you take draw from like p-stable distributions, you link it to the pth norm of those x's. Mm-hmm. Are there any connections between those kind of distributions and the ones that you?
I don't know exactly. So first of all, I can't claim that I didn't do this result. This was found on the net somewhere. It's like, you know, it's clever, nice. It's a nice, beautiful result. I think it's a really clean thing. I can't really say. So you're saying the p norms, right?
So in general, like if your size are drawn from a p-stable like Cauchy or normal or whatever, it relates to then you take the expectation, you get the 1 norm or the 2 norm of the x's. Yeah. So there is a connection there.
Yeah, there probably is. You know, the one weird thing in this, you know, when you relate this to matrices, you know, when you're doing with 1 norm or the 2 norm or these things, you're automatically putting absolute values on everything. So it may not directly be the same. I'd have to think about this, but that's one major thing. Like, we're not using absolute values on eigenvalues. We're using the raw eigenvalues themselves. So it doesn't necessarily seem to be directly connected to the sort of the standard norms that, as matrix theorists, we're used to using, where you always put absolute values on eigenvalues of Hermitian matrices. But I'd have to think about it to give you a better answer.
Thanks.
Hello. So you started out with looking at this notion of the combined length of all of the representations.
So when I was defining factorization lengths?
Yes, factorization lengths. And that obviously is very fruitful. We just watched a very nice talk on it. Was there anything in your research that used just like the number of factorizations?
Well, yes. I mean, it's a standard. The number of factorizations that pops up in the asymptotics in every formula. So the top formula here for the total number of factorizations, I don't know who proved it, but it's certainly a well-known fact in the numerical semigroup community. And that's a necessary ingredient in basically all the other formulas, because you need to normalize by that. So yeah, it does come up. I can't lay credit to it. I don't know who did it, but certainly that's the first step, because you need that to do everything else.
Thank you.
So sort of you say that like in your work you're trying to establish more of these like weird norms about like absolute signs using other sorts of like random variables like besides exponential. But then like when I was hearing the whole talk, it seems like there were some like properties of CHS polynomials that really tie into like how you can define a norm. So like in your own work, do you actually approach it with like the random variables first, or do you approach it with like a polynomial first?
Well, that's a great question. So how I got into this topic, as you can tell, it's sort of like all over the place, right? So a student just came back from an RU with Chris O'Neill at San Diego State, shout out to him, and said, I want to keep working on this for my senior thesis. So I said, okay, I'll learn about this. And so I first learned about this, and then we went on this long road where we'd get some new idea, and then we'd go in a totally different direction because it seemed like a cool thing to do. So at this point, it was like an aha moment, saying like, wait, there's nothing special about the exponential distribution. Why don't we just change it up and see what happens? And so my general philosophy has always been, I don't necessarily go into something saying I'm going to prove this result or I'm going to solve that open problem. It's sort of I go into things and tinker with things and see what comes from it. So we certainly didn't go into this sort of thing with more specific polynomials. We kind of had hopes that, hey, can we get this polynomial or not? And can we cook up the distribution? I think that we haven't completely answered that. What we've been doing is sort of saying that, oh, we're getting all these other cool polynomials of eigenvalues popping out of this if we use all the standard distributions. Because one of the first things you can do is just take a list of the standard distributions and see what happens. And there's a lot of cool stuff that comes out of it. Yeah, so that's the end we're sort of looking at. I'm just always trying to figure out where are new branches, what are new leads that I can follow, as opposed to, can I solve this problem specifically? I don't know if that helps.
It's certainly very thought-provoking to hear about your process. Thank you so much.
I want to thank Stephan for his great talk.